Hello and welcome back to MSE210, where we are discussing engineering measurements and data analysis. So this is week 2, and here we'll be doing a little bit more calculations. So if you do have a calculator, so now would be a good time to keep it on hand. So we will be doing some statistical analysis. So if you do have a calculator that's able to do that, that'll be great. If not, you can use a normal calculator still, but it's just going to be a little bit more amount of work. So without further ado, so let's get back to our topic of discussion. So the learning objectives for today are going to be to learn about display data graphically and to interpret these graphs, being able to recognize the measure and then different locations within the data, such as the center and kind of the spread of in some extent the spread of the data. Then we will look at ways to describe and calculate another measure for the data. So this would include the spread and then the mean of the data. And then we'll finally look very briefly at linear regression. So we'll get started here and then we'll complete the actual formulas and other things for the linear regression in the next video. So with that, so our topic for the day is we'll just do a very brief recap and then talk about plots, and then we'll go into all of these topics listed over here. So just a quick recap. Previously, we discussed why measurements are important. There are maybe just two main reasons or two main ways we use measurements in engineering. So the first way is kind of if you have a control system, so where you're trying to make sure that, say, for instance, if you're driving a car, so you want to make sure at a very high level, as a driver, you're acting as a controller here, and then you want to make sure you don't bump into anything else in the road, and then also you're maintaining the lane. And then within the engine, so you want to make sure that the engine parameters are maintained and all of that stuff. So we would use measurements in that area. The other place where we often use measurements, not in engineering and also in other sciences, is when you're trying to essentially improve the process or trying to change some parameter within the process and then trying to see whether or not you're having any benefit or you're basically changing the outcomes. So those are the two main areas, and then all of the other topics would kind of like fall very broadly within these two areas. After that, we talked about metrology, which is the science of measurements, and then we talked about three main types of metrology. So namely, we would have scientific metrology, which is the science of developing new techniques for the measurement. And then we have industrial metrology, where it is kind of application of all of the measurement techniques within industry or manufacturing center. And then finally, we have legal metrology. So legal metrology doesn't just mean that it's for maybe like litigation purposes, but it's more to do with kind of understanding between different industries as well as between different countries when you're doing some measurements and then you're basically transferring or selling some stuff. And towards the end, we looked at how very simple, seemingly simple mistakes can cause a lot of issues or near catastrophes. And we basically then examined kind of the difference between measurement precision, which refers to the closeness of data between one another. So what that means is if I basically take 10 measurements, so I want to see how much they're distributed. So they're going to be distributed kind of like, are they all clustered together? So that means that the measurement is more precise. The next term we looked at was accuracy. So this actually refers to how close the data is to the true answer. So if this true answer is over here, and then you have some cluster over here, the accuracy or the accuracy error is going to be this distance over here. And then if all of your measurements are clustered around the true value, then you're much closer to the true answer and your measurements are more accurate or considered to be more accurate. The next thing we talked about was repeatability, which is agreement of measurements made by the same researcher. So essentially you might make one measurement and with the same instrument and maybe not too much later, you're basically going to be doing the same kind of measurements again. So this is useful when you just want to make sure and then cover your bases. And the next topic we talked about was the concept of reproducibility. So reproducibility is essentially kind of an extension of repeatability, where the experiments are going to be done by another researcher. They obviously would use the same basic setup, so they'll actually need to tune and set the parameters the same way, but they might use a slightly different methodology, and then just make sure that the results are reproducible. So the repeatability and reproducibility of results are very important for scientific progress, because if your experiments and their results are both repeatable and reproducible, that makes it much stronger. So if somebody has done an experiment 100 years ago, you can kind of do the experiment again and then get very similar results within kind of the margin of error. After that, we were starting to look at the concept of probability, and then we had some definition there. So we talked about probability as being the science of likely, or the study of likelihood. And then within probability, we talked about population, which is the collection we wish to study. So it could be a collection of things, or collection of people, or collection of events. It could be any collection. A sample is basically a subset of the population. So obviously it may not be possible to study the entire population. So then we might pick few. So hopefully these are selected at random, and then we are hoping that these the sample that you select matches the characteristic of the bigger population. Then we talked about a variable which is notated by the capital letters. Typically you do X, Y, Z, and then if you need more variables, you may need W, V, and all of those, typically towards the tail end. So this is the characteristic of interest. So for instance, you could have like the height. So X could be height of the population, Y could be kind of the weight of the population, and you could have another variable Z, which could be something else related to the population. So then these are the variables of interest, and these variables could either be continuous, they could be categorical, where it could be, so for instance, you might be studying the eye color, so that doesn't really have any values associated with it, or the population preference for pizza versus sushi. So those would be categorical variables that you study. Or you can basically study numerical values. So in this case, it will be kind of the height of the population. So that will be actual numbers. Within numerical, these could be either a discrete or they could be continuous. And then the data that you collect would basically correspond to the type of variable. And then if you have, based on that, you can have either like the data that you basically collect. So if you're doing categories, you typically have like counts of those values. And then if you have numerical, you can do more interesting stuff. You can basically calculate kind of values for different parameters over there. And then we finally looked at different sources of error, data organization, and then ethics in experiment. And then we talked about where correlation does not imply causality. You could have multiple reasons where two variables or two phenomena are occurring together. So that basically just completes our recap. So moving on, so we are going to be looking at the next topic here. So we're going to be looking at plot, or how we'd actually graphically represent the data. So the first plot is what's known as a stem and leaf plot. So this is called a plot, but it's kind of like halfway between a plot and a tabular representation of the data. So the way it works is you basically take any number, and then you basically look at the number and then look at the last significant place. So when we talk about significant place, is we would have a little bit more discussion later on, but in these numbers, for example, that you have at the bottom, the last significant digit is going to be the last number over here. So this will be 0.1, 0.5, and so on. So we basically collect those. So we're basically going to take the number and then split that into the most significant part and then the least significant part. And then we're going to assume all of those are kind of like the same decimal place. So then what we do is we call the least significant parts to be the leaves. So those go into this box over here. And the more or the rest of the digits actually are the stems of our plot. So in this case, what we do is we can do a very, and then we basically draw a vertical line and then split them into two parts. So let's do the example here, which is example 2.2 in the book. So we have these numbers. So we can basically look through this. So this is 1.1 and then 1.5, and then we look through all of this stuff. So then what we have is for the leaf, for the stem number 1, we have here 1 and here 5. So we're going to load those down here. We can either add a comma or add a space here. Then we look at 2. So this is actually arranged properly, so it's much easier. So in this case, 2 is 0.3, 0.5, and 0.7. So we're going to put those numbers over here. Again, we are separating these by spaces. And then look at 3, it's 2, 0.2, 3, and 3. So we drop the decimal. So we note that here. And then keep going for 4. Even though this is 0, this is actually significant. So we note down as 0, 2, 5, 5, 7, 8. And so we put that over here. We move on. So the next one is 5. So it's going to be for 5, it's 5 and 6. So we note down that over here. And then 6, we don't have anything. Actually, 6 is 0.7. So we do 5 and 7. So 5 and 7. And then we don't have anything for the rest of it. And then finally for 12, we have 3. So the stem and leaf plot are useful in 2 ways. So firstly, it will give you the shape of the distribution. So you can kind of see how many digits are for each of the stems. So that will give you that more of them are clustered around 4. And then you can also see some gaps. So if I'd actually written down 6, 7, 8, 9, 10, and so on. So you'll notice that the graph basically drops precariously to 0. So then it might be useful where you might think and look at the data and say, maybe I have to take a closer look at this 12 because it seems to be kind of a little bit out of place. So that's where we would use the stem and leaf plot. To be honest, it's not very widely used. And so we will move on to the next plot. So the next plot is going to be a line plot. So this is useful for specific data values, and then they're presented in a data. So just let's look at an example. So this is going to be example 2.4. So just these are typically discrete data. So they're kind of like split and they have like distinct values. So in example 2.4, you have 40 mothers who are surveyed and how many times you have to remind the teenager to do his or her chores. And so these are the numbers that are collected. So number of reminders is 0, so there's 2, number of reminders 1, 5, and so on and so forth. So here, these are actually numerical values. So x is actually a number of times somebody is reminding, or it could also be similarly some categories as well for which you can do the line plot, but typically it doesn't really make sense in that case. So we can plot this. So what we do is take this 0, and then for 0 it's going to be 2, so that's going to be here. For 1 it's going to be 5, and so on and so forth, and then we can draw a line through it. So we have the line, and then we have the points here that we can actually draw and connect. So this is how we would create a line plot. So the next chart that we are looking at is the bar chart. We are going to basically reuse the same example. So then here, these are going to be like bars or columns separated from each other. So generally what we do is on the x-axis, we plot our the values. So in this case, it's 0, 1, 2 to 5. And then on the y-axis, we have the frequency. So what we can do is we can go back and then plot all of those values looking at the table there. So we get this kind of a bar chart, and then we can create the shape over here. So this can be used both for categories as well as numerical values. So for instance, here instead of 0, I can have number of people who like sushi. Here could be number of people who like pizza, and then here it could be number of people who like maybe pasta, and so on and so forth. So this bar chart would still make sense where you can basically put them in this column kind of a format. The next chart is essentially like a pie chart. So where you're basically going to take a pie or a circle and then divide it into pies proportional to the relative frequency. So what we mean by relative frequency is we take all of these frequencies and then divide by the total number. So in this case, the total number is 40. So we divide 2 by 40, 5 by 40, so on and so forth. And then we plot it over here. So we get a plot something like this. So typically you could represent this in color or in grayscale. So in this case, if you did it in color, so this would be like different colors. You can also shade it in different ways. So you can have one shading for here and a different shading for here, and then that will essentially distinguish between the different segments of the pie. So the next chart is we're going to be looking at a histogram. So this is actually very close to a bar chart. So here, so what happens is we essentially use this for continuous data, right? So previously we were talking about discrete data, so where you had like numbers. So mom cannot remind somebody like 2.2 times, so it's either going to be 2 or 3. But then if you're looking at say heights, then you can basically have a height of say 1 meter, and somebody could just be a little bit taller at 1.1 meter, so on and so forth, where in principle this is going to be a continuous data. So that's where we would use a histogram over here. And then what we do is we basically, again, we'd have similar to a bar chart. So this is going to be just an extension of the bar chart. And then what we do is this is used to kind of essentially identify data variation. So again, so we can basically take these continuous heights here, and then we can basically create a bar chart for this value over here. And then we can do the calculation. So now before we actually construct the frequency table, we need to take our data and then divide or partition the data so that we can create what's known as bins, or some boxes in which you're putting the data. There is not really a standard way of calculating these classes or bins, but then we will use a very standard or kind of like often used rule of thumb. So it's known as Sturge's rule. So it's kind of a little bit complicated. So or rather the formula looks scary, but it's just a rule of thumb. So we basically use the number of bins as 1 plus 3.322 log base 10 of the number of data points you have. We generally want to ensure that we have about 3 classes and no more than 20 classes. And generally then what we'll do is take the minimum of the data and then calculate the maximum of the data. So then we'll calculate the difference between the two divided by the number of bins will give you the bin size. Then we want to basically just make either like round the bin size to a nearest integer, which will make it nicer, or we sometimes might round it off to 0.5. Again, it depends on how you're constructing the bin, and then you might actually go a little bit back and forth, and you might need to try few options to see how your distribution actually looks. The next thing we're going to look at is we're going to talk very quickly about tally counting. You're probably already familiar with this. So the way it works is each time you count, you put a single slash for 1. If you count 2, you put a second slash. So if you have 1, you put this. If you have 2, you put 2 slashes, and then you keep going. And then once you hit 5, what you actually do is you put a cross across 5, and then it counts as 5. The data that we have actually has 60 data points with a minimum of 60 and a maximum of 74. Basically, if you use Sturge's rule, we get 7.664, and then we can get a bin size of 1.83. So we might want to round this up to 8, and then we can get a slightly smaller bin. Or what I would rather do is I'll round up the bin to 2, which will basically give me, or a bin size to 2, which will basically give me 7 bins. So that's what we're going to do. And then we're going to fill up the bin here. So we're going to exclude all of the minimum. So we'll fill in these values, and then we'll put the minimum value, the maximum value of the bin. So then we're going to do this. Just the 60 alone, we would actually count all the minimum points as well. So once we do that, we can count. So it give me a good time to pause the video and count all of these values. So if you did a tally count, you would get this. So I've used a horizontal slash here. So I have 5 here, and then this is 10, and then I have like 15 plus 3, and so on and so forth. So then once you have this, it's fairly easy to figure out. So this is 5, so I put in 5, and then this would be 10, so on and so forth, and then we can fill in the actual total counts over here. So once we have this, we can actually plot and then do a histogram plot of this data over here. So the way it'll look is, this is how your chart will basically look over here. So you can basically collect all of these values and then create the chart. So the way this is done is, so you can basically look at the data. So if you, The standard convention is when you have a square bracket, that means you're including both of the boundaries, and then when you have a semi or a simple brace or a simple parentheses, you're basically excluding the limit. So in this case, this is basically all values which are greater than 62 and less than 64. Again, if you really want, you can decide to include the data either on the lower end or the upper end, and then based on that, you might potentially change this chart over here. So the next data type we're going to look at is known as the frequency polygon. Here, this is analogous to the line chart. So we're going to look at example 2.2, where we have the lower limit and upper limit, and then the frequency, and then the cumulative frequency. So what we then do is for each of those values, we'll take the midpoint and then create a chart as such, and then draw a straight line to join all of those points. And so this gives us the frequency polygon. So the next type of data that we'll often see is the time series. So this could be like a horizontal, where the horizontal axis is basically an increment of time. So this data comes from the Climate Watch, where we are looking at the CO2 emissions per capita, and then you actually notice that Canada is reasonably high. If you do a similar plot for per or total amount of emissions, you would notice that China and India are higher than US and Canada. But again, you can figure out how you want to plot. But mainly, you're looking at the change over time. So that will be with time series. So this concludes this segment. So in this segment, what we learned was different ways of creating charts and then graphically representing data and interpreting the data. So now we are going to look at measures of data. So previously we essentially had, you can think of like a big box of numbers, and then now we are basically going to figure out different ways you can categorize data rather than into bins, which do it slightly differently. So the first measure or way we look at the data is the percentile. So when we say it's the pth percentile, so generally it will be like the height or the score. So that basically indicates that p percentage of the data or score are equal to or less than the value. So that means if you took the CAT or the another exam or an exam, and then they say you're in the 90th percentile, that means everybody has gotten a score. So for instance, if you had a score and then you got the 90th percentile, it means there are 90% of the people have gotten a score of equal to or less than that value. That means, so just to reiterate, so if your score, say you had 17 on 20, being the 90th percentile, implies that if you look at all the data, 90% of the score. So you count all the scores and then figure out how many of those scores are equal to or less than 17 out of 20. So that will give you the 90th percentile score in the test. So there is a chance that 90% of the students would have gotten 17, then still the 90th percentile would be 17. It could also be that you have just like one person who has 17 and then a whole bunch of people who got much lower scores, and still the 90th percentile would still be 17, right? It only talks about where you're basically cutting or like breaking up the data. So on a related note, this basically means that less than 10% scored over 17 out of 20 in the given exam. So the next data we look at is the median. So median is the center of the data. So if you have a distribution, you have different numbers. So you cut the data right in the middle. So that's called the median of the data. So this actually corresponds to the 50th percentile as well. Generally, what we can also do is we can divide the data into different quartile, which is basically 1/4. So what we can do is we can do the first quartile, which is denoted by Q1. This basically means you collect 25% of the data, and then you have a second quartile, which is the 50th percentile, and then you have the third quartile, which is the 75th percentile. So median, as I mentioned, is the 50th percentile here. So let's do a very quick example. So you're given this data here, and then you're going to determine the location of the median, and then figure out the values. So here there are basically 14 observations over here, right? So you can count these. So there are 14 observations, And so then the median would be basically the 7th position. So we can take a look. So these are actually ordered. So 1, 2, so you can count here. So you have 1, 2, 3, 4, 5, 6, 7. And then because it's an odd number of location over here, we are going to basically, or rather even, so that we're basically going to take the mean of these two values to get the median over here. So 14 observations, so the halfway point is going to be between 6.8 and 7.2, and then we'll take the mean of the two or the average. That will give us the median score. So the next concept we look at is known as the interquartile range. So this is the number that indicates kind of the spread of the distribution. So we basically look at the IQR, the short form, as the difference between the Q3 score minus the Q1 score. So an example would be, so if you, from the previous example, so if you had a, say in the exam, your first quartile was 5 out of 20, and then the third quartile was 15 out of 20, then your interquartile range is going to be 15 minus 5, which will be 10. So that will be the range over here. So the interquartile range is useful to determine basically kind of the potential outliers. So a rule of thumb is we basically look at 1.5 times interquartile distance, and anything that's kind of like below or above that, it could potentially be an outlier. So let's look at this 13 data points over here and then see if there is an outlier over here. So this would be a good time to pause the video and then do these calculations. So let's do these. So then we can order the data from the smallest to the largest. So we did that. This is the range that we get. So then we can count the data and then figure out where the median 20th percentile is, and so on and so forth. So the median comes over here. So the median is this value over here. And then we can figure out the Q1. So basically because there are 13, so then we can calculate 25% should be less than this. So that basically becomes kind of the Q1 will be halfway between these two values. So we take the average of these two. And similarly, we can calculate Q3, which is going to be the average between 639,000 and 659,000. And so we calculate Q3, and then the distance or difference between these two is going to be the interquartile distance. And then we calculate 1.5 times that value. So then we calculate 1.5 times this value. So this comes to 510,373. So then what we do is we calculate basically Q1 minus 1.5 times IQR. So then what we do is we calculate Q1 minus 1.5 IQR. So that will give you kind of the lower end of the extreme values. And then we look at Q3 plus 1.5. So if something is over 1.5 million, then it can 1.159 million. There's a possibility that it's an outlier. So again, no houses were below zero value, but however, there's a 5.5 million house, which is potential outlier here. So the next concept we're going to be looking at is known as the box or box and whiskers plot. So here, this is kind of a graphical representation of the interquartile and then the quartile that we basically did. So what we do is we basically pick 5 points. You're going to have the minimum value in the data, then the maximum value. Then you pick the first quartile, the median, and the third quartile. So you're basically going to have the minimum, maximum, and then arrange those values. So these will be in increasing order. So let's put those values up. So then what we do is we're going to draw a box between Q1 and Q3. Right? So you draw a box between Q1 and Q3, and then you mark the median in the box. And then we add a whisker to indicate the minimum and the maximum value. So this graphically illustrates the spread of the data. So it gives you another visualization of the data over here. So let's do an example. So you have this plot over here. So let's calculate or create the box and whiskers plot over here. So again, you can pause the video and give it a shot. So in this case, the minimum is 1, the maximum is 11.5. So the data is actually arranged in increasing order. So then we have the plot at the bottom. So I'm going to create the box plot. So you can calculate the median, the first quartile, so on and so forth. So the Q1 is 2, Q3 is 9. So Q1 is coming over here, and then Q3 comes over here, it's 9, and then the median is 7. So that's basically the average between these two values, and then we can create the box and whiskers plot over here. So the next concept we're going to discuss is the mean, variance, standard deviation of both sample and population. So the previous data that we're looking at, median, is with respect to the count. So if you have like different populations, so you're figuring out where the different fractions or segment of the population lies. So mean and median is basically kind of taking the average of the data. So there is a small difference between sample and population. If you recall, population is the entire data, so it's going to be everybody in like the city or in SFU or so on. The sample is going to be you picking some segment of the segment or a selection from the population over here. So the first one is a mean. So the population mean is denoted by mu, and the sample mean is denoted by x bar. So then we basically notice that mu is approximately equal to x bar is going to be the sum of all the data that you collected divided by the number of data points. So the variance or the variability can be denoted by sample variance. So the sample standard deviation denoted by S is the square root of the sample variance. So S is square root of, so you're basically going to do a square. So you're going to take whatever value you measured, subtract the mean from it, square those values, add all of the sum of the squares, but now you're going to divide by n minus 1, where n is the number of samples. So you're always going to subtract and then do the calculation for the sample, to calculate the sample standard deviation. And then what you can do is you can actually do some mathematical analysis, and then if you basically expand this out, you actually notice that this basically becomes sigma xi squared, and then you basically get minus n x bar squared. And then so this is actually a useful formula when you're basically kind of creating it as a table. So when you have a population, the standard deviation is denoted by sigma. So here, since you're taking more points, you're going to basically be dividing by n for the population standard deviation. So just a note, so this is different between dividing by n minus 1, which is the sample standard deviation, and then the population standard deviation over here. So let's do a simple example over here. So you have the baseball, the age for each of the players. So you can calculate, use either your calculator or do it by hand, and then calculate the mean, sample mean, and sample standard deviation. So here we have 25 points. So if you add all of those, you get 767. You divide that by 25, you get 20, or you can add the sum of the squares as well, which will be useful later on. So then you can divide 767 divided by 25, you get 30.68, which is the sample mean, also the population mean. So then we can calculate S squared using the formula that we had, we just mentioned in the previous slide over here. So we're going to use this formula or the n, which is a little bit easier to calculate. And then so what we do then is we get S squared is n, so you're just like multiplying all of this out, and then this x squared, and then you calculate those values, and then you get this to be 37.143, and then we take a square root, that will give you the sample standard deviation. So once you have that, you can calculate kind of what is x bar plus 2 sigma 2s. You can get this value over here, and then you can see that basically no value is greater than mean plus 2 sigma. So the next concept we're going to be looking at is kind of doing the same population standard, mean, standard deviation, etc. using a frequency table. So here the concept still extends, just that x bar, because you have frequency and the number of times things occur, you basically calculate x bar would be sum of the frequency times the mean of each of those blocks, and then you do the similar thing to calculate the standard deviation. It's going to be sigma is equal to 1 over square root of 1 over sigma f, and then you do sigma f mean squared minus x bar squared. So let's do the example here. So you have the class, so you have the range between 0 and 2, 3 to 5, so on and so forth, and then you have the frequency, so you can actually calculate and do these values over here. So you can calculate the midpoint. So this is going to be 1, and this is going to be 4, 7, 10, 13, and 16. So we can calculate f times m. So you're going to multiply these two. So you can calculate 1, 24, 70, 70, 0, because there are none here. So this becomes 0. And then we can do this to be 32. And then we can calculate the square of the mean here. And then we can multiply the square of the mean times the frequency and then fill in this box over here. And so then we can calculate x bar is going to be the sum here divided by the total number of frequency. So that basically becomes 197 by 26, so which gives us 7.577, and then we can calculate sigma. Again, so similar formula to what we had before, and then that gives me square root of 11.781, which is 3.432. So this concludes the segment, and then what we did in the segment was we talked about the different measures of data. So we talked about the percentile. The pth percentile basically says that p percentage of the score are less than or equal to the given score over here. And then we talked about the mean, the median, the first and the third quartile. And then we talked about the interquartile distance and the box plot. And then we finally calculated the mean and the variance. So next we move into a more interesting topic which will be relevant in many engineering applications. So what happens is in a lot of engineering applications you just don't have one data. Often you have things that you actually do. So you basically would take a length and then you pull it by a certain force. So you would have data for length versus the pull strength and all of that stuff. So you have like multiple variables, and then most of this could be like you have multiple variables and then you want to find the relationship between these values. So the most simple example would be try to find a linear relation or trying to apply a linear relation. So if you have something of the form y equal to a plus bx, so a would give you what's known as the intercept, and then b would be the slope of the line. So so if b increases, your slope increases. If a increases, you're moving the line up and down. So here's a simple example. So this is example 12.1. So you're given the rate and then like a one-time setup fee. So you're going to figure out what the cost is going to be and then create the equation here. So we can basically say x to be the number of hours it takes to complete a job, and then let y be the total cost to the customer. So then since there's a fixed cost and then there is a linear cost 32 times x, we can write the equation as y equal to 31.50 plus 32 times x. So that was basically the very simple linear relation. So next we're going to look at what's known as a scatter plot. So a scatter plot is basically you having two sets of data and then just creating a chart or a graph between those two values, right? So here you have the x values, which are years, and then y is the number of users, and then you can plot these values over here. So this is what is known as a scatter plot. So the next thing is trying to find talking about linear regression. So we're going to do just an introduction to this. So here what you're going to do is you're going to try to find a linear relation between the scatter plot and the actual data, right? So this is a linear relation. So if you give the different values, you can find the linear relation. In this case, you're given like either a set of data or graphs over here, and then we're going to find the linear relation. So let's do that. So we are just initially going to do only the stable 1. So let's plot those points. So you have 1, 3. So 1 is over here, 3 is over here, and then 2, 5, so on and so forth. Let's plot those values over here. And then these are very well lined up. So I can just create a straight line through this, and then my line looks like this. So the next step is I'm adding two more data points, 1.5, 4.5, and 7 and 13. So 1.5 is here, 4.5, this is 4, is going to be somewhere here, and then 13, 7 and 13. So 7 would just be outside the screen, and 13, 4.5 and 13. So 4.5 would be here, 13 would be here. So let's add those 2 points. So now you notice that the original line is no longer representing all of the data here. Right, so then this has a distance over here, this has a distance over here. So what we might want to do is actually move this line, maybe bisect this distance, move it a little bit high, and so then maybe go through point number 2. So this seems to have a better fit. But this seems more like just like guessing the values. So then we will look at a more systematic approach of doing this regression or figuring out where the line needs to lie. So before we do that, we need to understand a few concepts with respect to the regression error. So let's do that. So we look at how the error is actually calculated. So we have some unknown error. So you're going to assume that your y is actually a plus bx plus some error over here. And so then your error is basically a y minus a plus bx. So let's calculate these values. So given these, so I've tabulated both tables together. And then we have this equation here. We're going to calculate the error for the first fit and then for the second fit. So just if you recall, just if you go back to the line over here, so you'll notice that this line has the intercept over here at 1, and then you can figure out the slope. And so that's what we did, and then created, and then we're going to calculate the error over here. So if you put a equal to 1 and b equal to 2, and then we're going to use this equation to calculate the error. So we can calculate the values of a plus bx. So we do this, and then we can calculate the error as the difference between these, and then you only have an error 3 in the bottom 2. So we can do the same thing for the other case for a and b. So we do this. So obviously the errors are higher, but then we calculate the sum. So you'll notice that this error has decreased, but all of the other errors have increased a little bit. So with this error, we can, because these are like errors for individual measurements, so we have to do something more interesting. So what we'll do is we will basically kind of try to find a metric which aggregates these values. So the first one we're going to look at is the sum of the errors, where we're going to add up all of the errors. So in the case a equal to 1 and b equal to 2, if you add all of those values, you're going to add 3 and 3, you get sum of the errors as 6. For the second case, the sum of the errors was minus 2. The second thing we're going to look at is over here, this is what's known as the sum of squared error, because the sum of the squares doesn't really completely capture the variance or the actual size of the error. So what we'll do is we'll basically sum the squares of the errors. So this is called the sum of the squares of the error. So we do that. So for the first case, you just have like those two 3's. So if you square them, they get 9. So 9 times 2 is 18. And then for the second case, you do the sum, and then you have 6 1's, and then 1 squared minus 1 squared is 1, and then you have 2 2's, and then you add. So this basically becomes 14. So you notice that so it just up here, like if you go back, so that if you basically chose just the sum of the errors, that seems to essentially underrepresent all of the size of the error. So then we can actually calculate the, so if we divide these values by the number of counts or number of measurements, we'll get the mean sum or the mean square. And so this is what we can do. So this basically concludes this segment as well. So what we did here was we graphically created the line of the best fit, and then we were also calculating the sum of the squares and sum of the errors and sum of the squares of the errors. So this basically concludes this lecture, and then when we come back in the next lecture, we'll use the error metric and then try to figure out a good value for the regression line which minimizes the sum of the squares of the error. Right? Thank you.